Howdy. I'd like to spend about 10 or 15 minutes talking to you about how to do definite integrals with substitution. And to get at this, I'd like to take a look at a couple of problems from your book and from your packet. And the first problem is number 67, which is the integral from 0 to pi over 2 of cosine 2x over 3 dx. It's possible to do this integral with repair, and it is also possible to do it with a formal substitution. And so I want to do both of those to compare and contrast the methods. Repair is the easiest, so we'll start there. If I compute this integral by repair, there are no big surprises. Mentally, I identify 2x over 3 as my u. So my thought bubble is u equals 2x over 3, and du is equal to 2/3 dx. And so my integral is all ready for integration, except it's missing a factor of 2/3. And so using the process that we talked about in class, I multiply by 2/3 on the inside, and I divide by 2/3 on the outside so that my integral does not change values. And now it's a simple matter of fundamental theorem. This is cosine u du, and therefore its integral is going to be sine of u taken from 0 to pi over 2, which gives me 3/2 of sine of 2/3 times pi over 2 minus 3/2 sine of 0. And of course the 2's cancel, so that I have the sine of pi over 3. Using your unit circle, you can find out that the sine of pi over 3 is root 3 over 2, so that I get 3 root 3's over 4. By the way, if you did not know that value immediately, pause this video for about 5 minutes and practice marking up your unit circles so that you can do sines and cosines. Well, what if I did this with formal substitution? If I do this with formal substitution, then I'm going to walk through the same process that we have done. That is, I'm going to pick a u, and then I'm going to transform the integral in terms of u. The one thing that's going to be different is what we have to do with the limits of integration. We're going to have to transform them also. So here is my integral, and off on the side, I do my work of formally substituting. U is equal to 2/3 x, du is equal to 2/3 dx, and therefore dx is equal to 3/2 of du. And so now I come back to reassemble my integral in terms of u, and the integral is cosine u and 3/2 du. But now I also need to transform my limits of integration, because these current limits of integration are x values. I am integrating the curve y equals cosine 2x over 3 from 0 to pi over 2. Let's take a look at what that curve looks like. It's going to have a period of 3 pi, and we are integrating it from 0 to pi over 2. It's going to have an amplitude of 1. And so we're looking at the area of this region right here. When I do the substitution, I am transforming my curve into a new curve that will resemble the old one, but it's not going to be exactly the same. The curve y equals cosine u times 3/2 is going to be a cosine curve, but it has a period of 2 pi, not 3 pi, and it has an amplitude of 3/2 and not 1. So I'm going to need to change my limits of integration to reflect that fact. so that I end up with a net signed area that is exactly the same. How do I do that? Well, it's actually very easy. Since u is 3/2 x, I'm going to evaluate u at the lower limit of integration, and I'm going to evaluate the u at the upper limit of integration. Two-thirds. There we go. I knew I was doing something silly. Which gives me pi over 3. And these new u values are now going to be my new limits of integration from first to last. Please note that they correspond exactly. So if I accidentally happen to get a new u value in the bottom that was larger than the u value at the top, that doesn't matter. I'm still going to do the one that corresponds to 0 goes here, and the one that corresponds to pi over 2 goes here. Well, this integral by itself is now a value that represents the net signed area under the curve of this guy, of this region right here, which has the same area as the original region. And so that's actually good news for us. We did a little bit of extra work in finding new limits of integration. Having done that, we have relieved ourselves from the burden of back substituting. Because I can evaluate this integral directly from u equals 0 to u equals pi over 3. And look at that. When I do, I get sine of pi over 3 minus 3/2 sine of 0. And that's exactly the computation that I had up here with the repair. That will always happen. It will always be the case that when it comes to the numerical evaluation, I will end up with the same values, first and last. So what's the moral of this story? When we are formally substituting, we choose a u, and we compute du, and then we replace everything in the original integral in terms of u, including the limits of integration. If you are disciplined about not having mixed forms so that you don't have u's and x's together in your integral, then this will be fairly easy because you'll have the mental picture that in your new integral, everything has to be u's, including the u values for the limits of integration. Let's do one more quick example in which we will see a surprise. And that is going to be number, where did it go? That's going to be number 53, the integral from -1 to 1 of x times x squared plus 1 cubed. And that's slightly wrong. dx. Now I could do this with repair. I'm not going to do that because I don't want to spoil the surprise. I'm going to skip straight to the formal substitution. I'm going to let u equal x squared plus 1, the inside function. And therefore du is equal to 2x dx. And I can observe that I have the du sitting right there, except for the factor 2. Let me move my scrap work to the side where it belongs. And so x dx is equal to 1/2 of du. And now I'm ready to begin assembling my new integral. I'm going to write this as the integral of u cubed times 1/2 du. For the limits of integration, I need to evaluate u at the lower limit and at the upper limit. When I evaluate u at the lower limit, I get negative 1 squared plus 1, which is 2. And when I evaluate at the upper limit, I get 1 squared plus 1, which is also 2. And there's my surprise. Because this is the integral from 2 to 2 of whatever, I don't even need to work hard. The value of that integral is 0, and I'm done. How did that happen? Is that really right? Well, as it turns out, it is. If I take a look at the graph of the original region, which is y equals x squared plus 1 cubed, then the graph looks something like this. And as I go from negative 1 to 1, I observe that what I have is an odd function. And that odd function is going to necessarily have net signed areas to the left of 0 and to the right of 0 that are equal but opposite, so that when I add them together, the net signed area is equal to 0. When I pulled off the substitution, that substitution took my region and it transformed it into a new region, 1/2 of u cubed, with a graph like this, whose area was the same. And that area was 0. And that's the end. So, moral of the story, when you substitute everything in terms of u, including the limits of integration. And finding the new limits of integration is simply a matter of evaluating u at the lower and upper limits. Repair is different. Conceptually, it's a little bit simpler. With repair, the integral is never changed into u's, therefore the limits of integration are never changed into u's either. We use the x values because we are doing an integration in terms of x. I hope this is helpful.